chemists and a specialist in scanning probe microscopy, and very distinguished scientist. I'm very lucky to be able to collaborate with him. And we've been working together now for probably almost 20 years on this and other topics. And so in addition to the synthesis and the measurements, it's important in this area to have some collaboration with theoreticians who can at least try to rationalise some of the results that you've got and make sense of them. And so we collaborate with a group at the University of Lancaster mainly for that. And that's very convenient for us because it's a 1 hour drive on the motorway, so we get to see each other quite often. And in addition to that, we have some international collaborators who I've listed here, some of whose names you will hear during the course of the presentation. And most of the work that I'm going to talk about today was done by Dr. Ed Leary, who's pictured here, and Dr. Sarah Chappell, who's pictured here. Some of it has been done more recently by Dr. Andrea Bazzoli, who's graduated with a PhD from my group last year. And our work has been funded by the British Engineering and Physical Sciences Research Council in England. So that's the acknowledgements. Here's the overview of the talk. I'm going to begin with an introduction where I'm going to try and explain what molecular electronics means, how we make the measurements, and how we analyse the results statistically. Then I'm going to look at two particular stories, and if it seems to you that in this work we've kind of blundered about from one result to another, and this is because this is the way science works. So I don't like to try and paint a glossy picture that everything worked well. I'm going to tell this story the way it happened. So I'm going to talk about some work where we've used electrochemically active molecules in our single molecule junctions. The idea being that we want to be able to switch the electrical properties of those molecules using some kind of external force or event. This is the way in which we hope eventually we'll be able to get some kind of electronic function out of molecules. So that would be the first part of the talk, and then an adventitious discovery that was made as a result of this work has evolved into another topic. I'm going to try and describe how we are hoping to be able to make single molecule sensors using a phenomenon that we've discovered fairly recently. So, if I say to you molecular electronics, some of you may think of organic electronics, because early in the history of this field, the two terms were used interchangeably. Molecular electronics meant using organic molecules to perform an electronic function. But more recently, the field has diverged in a sense, and really the field of organic electronics, by organic electronics, is usually meant electronics devices which use substantial amounts of organic matter in thin films of one form or another. And here the important thing is the material properties of the organic substance, how the molecules can communicate with one another in the device. Because in order to get these devices to work, you have to push charge through the material. And in organic materials, this is not straightforward. And what you have to do is to try to optimize the ability of these materials to carry charge. And the charge has to go, of course, not just through one molecule, but through many, many molecules. And so the important parameter you have to control is how to get the charge from one molecule to another. Now, this field began, essentially, back in 1990, with the publication of a paper in Nature by a group based at the University of Cambridge, led by a gentleman called Richard Friend, who's a physicist, and his collaborator in the chemistry department, Andrew Holmes. And what they discovered, what they were doing was, Andrew Holmes' group had recently made a new kind of organic semiconductor, and this was a conjugated polymer, that's to say, a polymer where there are alternating double and single bonds throughout the material, so conjugated. And this was a new development really then. And this polymer was unusual in that it was stable to the atmosphere, and this had not been done before. And the polymer was called polyphenylene vinylene. And because this is a semiconducting material, they decided to try to make some diodes with it. So Richard Fran's group took some of this polymer on an ITO-coated glass substrate. That's a conducting glass substrate, and that turned out to be important. And then they made a layer of the polymer on top of that, and then they put a layer of aluminium metal on top of that to act as the second metal contact, and then they put a voltage across the device. And what they found was, if they applied a negative voltage to the aluminium and a positive voltage to the indium tin oxide coated glass, yes, the material acted as a diode. It allowed current through in that direction, but not if they turned the potentials the other way around. So it acted as a diode. But that was insignificant compared with the fact that when they biased this in the forward direction, they saw a dull greenish yellow light come out of the conducting glass electrode. So if they hadn't used the conducting glass electrode, if they'd used some metal, they may never have seen this. So it was an adventitious discovery. So this discovery that you could make an organic light-emitting diode with a conjugated polymer, that started a whole new field. And in the last few years, this has resulted in commercial products, some of which you may be familiar with. So display screens of some current generation of mobile phones, these full-colour, very bright, very sharp display screens, these use organic molecules as the light-emitting element. Some other applications of organic electronics, photovoltaic devices. So some of these conjugated polymers are extremely strongly coloured, so they absorb light very well. And if you make a device that is the opposite of an organic light-emitting diode, where instead of applying a voltage and getting some light out, you shine the light on the device, and get some current out, well, that's an organic photovoltaic device. And some of these materials are doing very well in these devices now. And the great thing about these devices is because they're made with plastics, then you can deposit the device on a flexible substrate. So in principle, you can make foldable photovoltaic devices, which you could use, for example, in architecture to coat buildings much more easily than with silicon. So that's something that may come along soon. So that's organic electronics, and as I say, all of these devices which are coming onto the market now, they rely on the use of quite thick films of material, and the charge has to get a long way through the material. In molecular electronics, we're trying to do something which at the moment is a lot more blue skies, a lot more futuristic, and that is to use the properties of an individual molecule to perform some kind of electronic function. And one of the early workers in this area, somebody some of you may know, A.P. De Silva, who's a Sri Lankan chemist who's working at the Queen's University in Belfast. And so this is an example of the sort of work that his group has been doing over the years. He's been making organic molecules that are designed to mimic the action of a known electronic device. So in this case, he's trying to imitate an electronic device called an AND gate. And in an AND gate, you have two signals that are applied to the gate. If both of those signals are, for example, 1, then the output will be 1. But if one of those signals is 1 and the other 0, or both are 0, then you only get a 0 out. So it's called an AND gate. You need both inputs to be the appropriate value before you get the positive output. And so in this molecule, how's he imitating that? Well, he's got this group here, which is called an anthracene, which is a fluorescent molecule. If you shine a UV light on anthracene, you'll get a blue glow. But this particular molecule, which is an anthracene with a couple of other things attached, this is not fluorescent. And it's not fluorescent because of a phenomenon called photo-induced electron transfer. So UV light will still excite this molecule, but the excited state is quenched by photoelectron transfer before it can have a chance to emit blue light. And it's quenched because of the presence of this amine group here and this crown ether group here. Now this amine group, you can turn that off by adding some acid, because acid will protonate that amine and its lone pair of electrons will no longer be available, and so that will kill the PET from the amine. This is a crown ether, which is a ligand which is designed to bind an alkaline metal cation, in this case sodium. So if you add some sodium to this as well, the sodium binds in this cavity here, and then, hey presto, the molecule becomes fluorescent in the blue again, and you can record a fluorescence spectrum. So these spectra down here, which are almost non-existent, is the light emission from this material before the two other things have been added, and this red line is the light emission in the presence of both sodium and protons. So this is kind of imitating an AND gate. Well, that's all very well, but of course, to get any electronic function out, we have to have this molecule wired into a device. It has to talk to other molecules, perhaps, or other electronic components. And an early piece of work in this area, or aimed at this, was a work by some theoreticians, Mageswaran and Ratner, and this has become a very famous paper now, although when it was published it was rather obscure, and it remained almost unsighted for about 10 years. And so this is really a thought experiment. Now, what Mageswaran and Ratner conceived was, if you had a molecule structured like this, so that you have a very, very electron-deficient part of the molecule here, and a very electron-rich part of the molecule here, and a non-conducting tunneling barrier part of the molecule in the middle here. If you were able to put this into a sandwich structure with a metal contact here and a metal contact here, then it wouldn't take very large bias voltage if you made this side of the molecule, this side of metal here negative and this side positive, because this molecule, this part of the molecule wants to be oxidized and this part of the molecule wants to be reduced. And so an electron will go from this electrode into this part of the molecule, and an electron will come from this part of the molecule and go on to the other contact. So it will leave this part positively charged and this part negatively charged, and then if the driving voltage is sufficient, the electron will be able to get from one side of the molecule to the other, and so the current will flow. However, if you try to do it the other way around and make this side negative and that side positive, you'd have a much harder job bringing this molecule into resonance. You'd need to apply a much larger voltage to drive the current through. So in principle, a molecule like this, an unsymmetrical molecule like this, could act as a molecular diode. And this was the first suggestion that a molecule could act as a diode. But as I say, these were only calculations. So for a long time, it was not possible to do this kind of thing. But at around the turn of the century, several techniques evolved at the same time, which enabled scientists actually to make and address metal-molecule-metal junctions. And one of these techniques was scanning tunneling microscopy, which is the technique that we use in Liverpool. So let me say a little bit about this first. So in a scanning tunneling microscope, what you have is a conducting surface here, and a conducting tip here, and you use piezoelectric crystals, which are very, very precisely able to control the position of this tip. So you bring the tip very close to the surface, close enough that electrons with a voltage applied, electrons can tunnel across the gap. Electrons are both waves and particles in quantum terms, and so they're able to do this phenomenon called electron tunneling. They can get across a vacuum gap. However, electron tunneling is a very distance-dependent phenomenon. The tunneling current decays exponentially as a function of distance. So if you retract this tip, then the conductance will decay very rapidly. But if you control the position of the tip and move it up and down on the surface at a fixed distance away from the atoms in the conducting surface, this technique is so precise that it can map the positions of the orbitals, the electrons' density in the surface atoms. And so what STM is most famous for really is the production of these really beautiful images that people tend to fill their surface science papers with these days. It's a very useful surface science technique for characterizing conducting surfaces by imaging. However, and it won its discoverers the Nobel Prize in 1986, Nobel Prize for Physics. However, as well as imaging, it's also possible to use the STM tip with appropriate conditions to either push atoms about on the surface in a controlled way, or even to push molecules around on the surface. And these are two images taken from the work of Donald Iger, who is a scientist at IBM Almaden in the States, a winner of the Kavli Prize for Nanoscience. This is one of his pictures of an experiment where he's pushing iron atoms around on a copper surface, and by corralling the iron atoms into a circle, he produces standing waves of electrons in the surface of the copper, which produce a large enough effect that they can actually be imaged by the STM tip, and it rather looks like what happens if you drop a pebble in a pond of water. And this picture here, which is quite famous, it's a rather trivial experiment. It's a stick man that's been made by manipulating carbon monoxide molecules on a platinum surface. So we developed this idea of manipulating molecules into a technique for measuring single molecule conductance. So as I said, in the STM experiments, if we bring a gold tip close to a gold surface, such that tunneling can occur, and then we disconnect the feedback loop that controls its position with respect to the surface, and then we retract the tip, so we move it up. Then what happens if we measure the tunneling current is the tunneling current falls exponentially, which is in accord with what you'd expect. It's the whole basis of the STM technique. Now, if we, instead of using a clean surface, we use a surface that's coated with some molecules, and these molecules have two contact groups on them, which are capable of binding to the gold, and typically these are sulfurs, these are thiol molecules. Then occasionally, when we retract the tip, we get a rather different signal. We get a larger current as a function of distance, and typically this gives a plateau. So as we continue to retract the tip, the current remains almost constant for a while, and then suddenly it decays away again. And this is consistent with the idea that we're lifting the molecule up in the junction, and at some point, if we continue to retract the tip, then of course the junction has to break. So what we do is we do this experiment many times to get a statistical picture of what's going on, because each junction is very slightly different. The way the sulfur binds to the gold atoms may be slightly different from one molecule to another. So we do this experiment typically thousands of times, and we compile the results into a histogram. And this might be a one-dimensional histogram such as this, where we see peaks corresponding to places or typical currents that are produced by these plateaus. And we interpret this as being due to the current through the molecule. And the current at the smallest current value here is typical of conductance through one molecule. Sometimes you get junctions with more than one molecule in, and we can see multiple values of these peaks at multiple values of a particular current. So one of the questions that you might ask at the beginning is, how do molecules conduct charge? And you'd expect a small molecule, less than, say, 4 nanometers long, you'd expect tunneling to be the dominant phenomenon. So this is tunneling of an electron wave through a barrier. And if that barrier is afforded by a molecule, then the structure of the molecule is important. The length of the molecule controls the width of the barrier. And the height of the barrier, how difficult it is for the electron to tunnel through the molecule, is controlled by the structure of the molecule. Because in physics, it's a rule that if you have two metal contacts, the Fermi energy of the system, which is where the electrons have to come from in tunneling, the Fermi energy has to lie between the HOMO and LUMO of the molecule. And so if we make a molecule that is conjugated and has a small HOMO-LUMO gap, we would expect it to be more conductive And if we use a molecule that has a large bernal-LUMO gap, like an alkane dithiol, we wouldn't expect it to be very conductive at all. So experiments have been done with very sophisticated solid-state devices where you use two contacting electrodes with a molecule between them, and then you try to bring a third electrode close enough to the molecule that it's affected by the electric field that is got by applying voltage to that third electrode. Now this is technically possible to do, but it's extremely difficult, and you need a fairly sophisticated solid-state setup to do this. And typically these experiments are conducted by physicists at 4 Kelvin in a helium cryostat. We don't have a helium cryostat, but we do have an electrochemical cell. So this offers a much more straightforward way of dealing with the problem, because now, using the properties of electrolytes, we can have our third electrode thoroughly remote from the other two. It doesn't have to be really close by. We can simply use the electrochemical potential to control the redox state of the molecule. So we can have a redox active molecule that's sandwiched between our gold surface and our gold tip, and we can control the potential of the medium. And the important thing is that with the right conditions, you can do scanning tunneling microscopy even under an electrolyte solution, such as a salt dissolved in water, or better, an ionic liquid. And we did these experiments at first with a molecule called viologen. This is a 4,4' pyridinium salt with an alkane thiol contact attached at either end to enable it to contact gold. And what we found was that we could change the electrical conductance of the molecule by controlling its redox state. So this molecule is redox active. It can be reduced in 2 1-electron steps. And in the first 1-electron step, if you add an electron to this molecule, you get the viologen radical cation. So at potentials where the viologen is in its 2+ state, the conductance is quite low, and at potentials where it's in its radical cation state, the conductance is about 6 times higher. And you can see that it slowly changes in this sigmoidal way as we go from 0.6 volts here to minus 0.4 volts there. That's a volt difference. So this conductance slowly changes over a potential range of about a volt. And for various reasons, that was quite a surprise to us at the time. And we decided to make some other redox active molecules and see how they behaved. And one of the molecules we had was this Pirolo TTF. This is the complete opposite of the viologen. It's a very electron-rich molecule, it's neutral, and we can oxidize it in 2 1-electron steps. And in the first 1-electron step, we go from the neutral state to the radical cation state again. But in this case, the molecule goes from the neutral state with a fairly low conductance, and then as we approach the redox wave, as we get to the halfway potential for this redox couple here, the conductance rises, but then as we continue to increase the potential, the conductance falls again. So we get this peak in the conductance over potential relation, which is rather different behaviour. And incidentally, I'm emphasising here with these other pictures that this experiment is quite hard to do. It takes a long time because we have to do our STM experiments at many different potentials with the same molecule. So this takes quite a long time. So how should these molecules behave? Well, all the theory suggested that they should behave like the Pirolo TTF. This is the theory from Kuznetsov and Ostrup, 2 theoreticians who worked on this area even before experiments in this field had been done. And they predicted that you should get a peak that coincided with the redox potential of the molecule. And that's what we saw for the Pirolo TTF. So for the Pirolo TTF, our experiment fits their model very nicely. However, for the viologen, it doesn't fit their model very nicely, or at least it didn't fit their original model very nicely. So Jens Ostrup went away after we published that first paper, and he modified his theory using our data and published a big paper in the Journal of Physical Chemistry, only about 10% of which I actually understand. But he showed that if you play about with the parameters in his model, you can actually account for that sigmoidal dependence, but it's a fiddle, really. So one of the suggestions that have been made as to why the two molecules are different is that the pyrrole TTF is actually rigid. The redox group is rigid in both of its redox states, whereas the biogen is not rigid in both of its redox states. So what we then did was we decided to make some more molecules that would be rigid throughout their redox chemistry and see whether they behave like the dinogen or like the pyrrole TTF. And to do that, we moved to some inorganic complexes. So some of you may have heard the fact I'm a coordination chemist by background, so I like making molecules like this. Any excuse and I will make some coordination complexes. So we made some of these terpyridine ligands that have a pyridine, an extra pyridine group on the end here, and this is useful because this is a good contact for gold electrode as well. So we could make many different metal complexes that are redox active, and we could use these pyridine groups to contact the metal. The other good thing here is that if you're working in a multidisciplinary field and your students are both synthesizing molecules and doing measurements, it helps if the molecules are easy to make, because they're not necessarily specialist synthetic chemists. Unfortunately, these ligands are easy to make. They're just condensation reactions, mainly. So we made a whole range of molecules. First of all, we looked at the dependence of the conductance as a function of length, and this was to enable us to see whether they're conducted by tunneling or hopping in the way that I described at the start. So we could build different molecules with different numbers of these phenyl rings in the chain, with either pyridine as the contact group, or these methyl sulfide groups, which can also contact gold. And we looked at the dependence of the conductance with length, and what we found, rather to my surprise, was that actually the conductance fits a reciprocal length relation rather better than it does a log or an exponential type relation. So at first glance, these molecules appear to be conducting at least partially by hopping, because their conductance falls linearly with length. Moreover, that slope beta, if we do force the log plot to be linear, then the slope of that line only gives a beta value of 1 per nanometer. And other workers had shown with organic oligophenyl molecules, so in other words, varying the length of the molecule by changing the number of phenyl rings in it, they'd shown that beta for organic molecules like that was about 4 per nanometer, which is much higher. Now, a low beta is often a first hint that the molecule is conducting by hopping and not by tunneling. So both of those things tend to suggest that these molecules conduct by hopping. We then looked at the electrochemistry of these molecules, and we had to use an ionic liquid for this because at least the ion complex here will not be stable in water at both redox potentials, in both redox states. So we used an ionic liquid. And you can see here that the electrochemistry for both of these, for this cobalt complex and this iron complex, is really perfectly chemically reversible. And that's important because to do these experiments, as I said before, it takes a long time and you have to be very confident that the molecule is stable in both of its redox states. So that confirmed that. And then when we looked at the conductance over potential relation, we found that it was in accordance with Kuznetsov and Ullstruck's theory. So we were very happy with this because we got this peak-shaped dependence of the conductance with the over potential. It rises as we get to the halfway potential for the redox system, and then it falls again for both of the complexes. And as I say, we were happy with this because it appeared to confirm this theory that if you have rigid molecules, they should obey that rule. Well, while we were doing this work, another group published a paper in JACS which was not on this topic, but which happened to use an osmium terpyridine complex here, and they looked at the conductance of this as a function of potential across the osmium 2, osmium 3 redox wave, and what they found was a sigmoidal relation that looks just like our biology from 2003. So our theory has a hole in it now, or at least it appears to, because in this case, this osmium complex is isoelectronic with our iron complex, osmium and iron being in the same group of the periodic table. So there's no good reason why this complex should be different from our iron complex. So that forced us to have another think about what was going on here. My colleague Richard Nichols was responsible for this. He had a sabbatical and he was able to actually sit down and think, which is becoming a rare commodity these days in British academia. And what he came up with was the idea that it's not so much the structure of the molecule that is controlling this behaviour, it's actually more the medium. Okay, it's the electrolyte medium that the molecule is in. So we went back and we took our biogen and we studied this again in ionic liquid. Because remember, the biogen had previously been studied in an aqueous medium. And what we found was, when we used the ionic liquid, the behaviour of the biogen was exactly the same as the Perella TTF. It occurred over a much narrower voltage range, and it shows this peak relationship between the conductance and the electric potential. So in fact, in ionic liquid, it behaved like all the other molecules. So this suggests that the behaviour that you get is not so much dependent upon the structure of the molecule, although it must be to some extent because the Perella TTF shows this behaviour in water as well. It's also dependent on the nature of the medium. So these are the conclusions to the first part of the lecture. We can indeed control the conductance of single molecules using electrochemistry. However, the on-off ratio is rather small, between the factor of 3 and 6, which is not going to excite anybody who's an electronic engineer. So that's something which we could improve. And the form of this conductance over potential relation is dependent on the medium and not so much on the structure of the molecule. Another thing that it shows is that ionic liquids are really excellent media for doing these electrochemical scanning tunneling microscope experiments. Okay, so I mentioned that the second part of the talk was on a topic that was an adventitious finding from the first part. So let me explain that. So these are the conductances in nanosiemens of these molecules in their off state when they're conducting purely by tunnelling. And what we noticed was that the conductance was really quite high when we looked at plain alkane dithiols. If we take this molecule here, which has got two C6 chains with a biogen group in the middle, if you imagine chopping the biogen group out of the molecule and then joining the two chains back to back, you would get dodecane dithiol. And we were able to measure the conductance of dodecane dithiol, although only just because it was right at the limit of what was possible. And that was 0.012 nanosiemens. So in other words, it's more than an order of magnitude smaller than the conductance of these molecules. Now if these molecules are conducting by tunnelling, they are even longer than dodecane dithiol because they have the extra pyridine rings in the middle. And yet their conductance is an order of magnitude higher. So there's obviously something strange going on there. We thought it might be something to do with redox group, but we really had no idea back in 2005 or 6 when we discovered this. We had no idea why this was. And so the first thing that I did was to make this simple benzene derivative. Now benzene is not redox active in any conventional sense, so this could not be a molecule that was affected by redox chemistry. And yet this molecule has a conductance of 0.7 nanosiemens. It's in the same ballpark as these other two. And we showed electrochemic by trying to gate the conductance of this molecule electrochemically that it does not respond to electrochemical gating at all. Okay, its conductance doesn't change as a function of redox potential. So what's going on here? Well, another thing that we did was, first of all, to play with this. I'm a synthetic chemist, so that I always resort to making new molecules whenever I can. So we made some substituted benzene molecules, and we showed that the conductance of these molecules depended on the nature of the substituents. If you have an electron-rich group attached to the benzene ring, the conductance is higher. If you have electron withdrawing fluorines, for example, the conductance is much lower. So that seems to suggest that whatever's going on, it's a pi bonding orbital in the benzene that is responsible for the conductance boost. Because when we put electron donating groups on, that brings the pi orbital closer in energy to the Fermi energy of the metal. And what we suggested was the model for this was molecular double tunneling barrier. It's known in solid, in inorganic 3-5 semiconductor devices that you can make sandwich structures of 3-5 semiconductors where you can control the band gap of the 3-5 semiconductor by changing its composition. So if you make a sandwich structure with two layers of a wide band gap, yes, that's right, 2 layers of a wide band gap semiconductor, okay, and then in the middle, a little filling of a narrower band gap semiconductor, and then if you apply voltage across this barrier, the current is much higher than if you take this narrow band gap semiconductor out and just join the 2 wide band gap semiconductors back to back. So even though the layer will be thinner if you did that, the current is much lower. So our molecules seem to be imitating that behaviour. So you could say that the alkane is a wide band gap semiconductor with a high barrier, and the high conjugated unit in the middle is a low band gap semiconductor, so it's acting as a well in one of these double tunneling barrier structures. So we decided to play about with the nature of the well. And for this we used oligothiophenes because it's easy to make oligothiophenes of different lengths, different numbers of thiophene rings. And we made molecules with 1, 2, 3, or 5 thiophene rings sandwiched between these alkane thiol units. And then we looked at their conductance. And what we found was that the molecule with 1 thiophene ring was a bit lower in conductance, and all the others are about the same. They're all around the 1 nanosine level. So even though we're making these molecules longer and longer by building extra thiophene rings in, their conductance doesn't really change, and that's quite surprising. And our first idea as to why this might be was that if you increase the length of the oligothiopene, okay, you are making the molecule longer, and that should decrease the conductance, but you're also making the centre of the molecule much more conjugated, so you're lowering the pi star energy separation by making that part of the molecule longer. And so that should raise the conductance by making it a more effective well. And maybe those two things are just offsetting each other, and it happens that they cancel. And we would have been happy to publish that, but we decided to try to get some theoretical confirmation. And this was actually the first case in which we collaborated with Colin Lambert and his group at Lancaster. Anyway, they took a while to do some calculations on this system. And what I was hoping was that they would agree with us and we could publish a nice high impact factor paper and everybody would be happy. But as so often happens if you would associate with physicists, they tell you that you're wrong and that actually the conductance ought to decay exponentially with length. Okay, so even in this field, you couldn't really pretend that there's good agreement between our experiment and their theory. So then we had to think, why is our experiment different from their theory? Well, they're physicists. So when they do their calculations, their calculations are done effectively at 0 Kelvin, and they're done in a vacuum. So there's nothing surrounding the molecule, it's just there isolated in the junction. And that's not the case in reality, because our measurements are done at room temperature, and they're done in a normal atmosphere in the presence of water and oxygen and other things. So then, we gave the physicists the challenge. Look what happens to these thiophene rings if you have water there, because there's water in the atmosphere. So they did, and they found in their calculations that the water should weakly interact with the thiophene ring in a sort of hydrogen bonding manner, so the delta positive hydrogens of the water interact with the pi cloud of the thiophene ring. That's the main interaction. When that happens, although that's a very chemically weak interaction, only a few kilocalories per mole, it has a major effect on what these physicists call the transmission functions for these molecules. It shifts them all. It shifts all the peaks in these transmission functions. And that's enough to raise the conductance of the molecules when they're more conjugated.